Hello, everyone. My name is Alan, and welcome to yet another Tech Talk in our series sponsored by Single Sprout. Today, we have the pleasure of having Leo Crossman speaking about database management. So without further ado, I'm passing it to you, Leo.
Hello, everyone. Thank you for coming to my talk on database management. I would like to start off by giving a big thank you to Single Sprout for sponsoring this Tech Talk. Be sure to check them out at singlesprout.com. I'll start off with a little bit about myself. I enjoy watching technical talks in my free time, as I find it to be an incredibly streamlined way to learn a large amount of information in a short amount of time. One of my favorite technical talks, all of my favorite technical talks have one thing in common. The speaker introduces the topic, lays out the flow of ideas with the order they appear in, and then takes the audience along with them through the newly defined presentation schema. I love when, as an audience member, I can clearly see how each topic relates to each other, and I can understand the ways in which the ideas presented can scale to any size or dimension. Luckily for me, there's a significant overlap in the way these technical talks are laid out and the way in which we design databases. Let's go through the database management, or DBMS, topics we will address today. We will begin by defining some simple key terms. These will provide us with a strong foundation upon which we will build our understanding of DBMSs. After we have defined these surface level terms, we will dive deep into some more nuanced aspects of DBMSs. These will be referenced throughout the talk. After we have an understanding of what underlies all operations in a database, we will address the basic issues with these interactions and what happens when they run in parallel. Once we add that to our understanding, we will go over database storage structures and how they allow us to store and retrieve information in a way that is convenient and efficient. We will then move on to some important questions to consider when determining how to design your database. After these questions are introduced, I will explain why a database management system is the most optimal tool to use for storing large amounts of data. Once we have a strong understanding of the building blocks of a DBMS, we will transition into discussing some of the trade-offs associated with the various decisions made in database management. Now that you know what to expect from this talk, let's dive into some definitions. Starting us off, we have data. Data is raw, unprocessed facts. What about when we process this data? Processed data is known as information. What about pieces of data that rely on data stored elsewhere? This question brings us to schema and relations. Relation schema define the design and structure of all data and how it is used across columns and tables of a database. If we had more time today, we would go into detail on some common design patterns to consider when defining a database schema. What is a database? A database is a collection of related data. What about a term for describing the way in which we structured our database? Enter metadata. This is information that describes how the database is organized. An example of metadata would be a schema. Now let's move on to some core properties of a good database. A common phrase you will hear is ACID compliance. What does this mean? In short, a database that is ACID compliant will guarantee data validity despite power failures, errors, etc. Rather than discuss these properties individually now, let's take a look at the actual operations on a database. We will build our understanding of these operations to understand how a DBMS is ACID compliant. What are these operations called? Transactions. This is a big one, and perhaps the most important term in this talk. A transaction is a set of logically related operations. Put simply, a transaction can be defined as any one execution of the program in a DBMS. Transactions are used to manage concurrent calls for data in different parts of the database without worrying that these calls interfere with each other. Transactions are also the tool we use for recoverability, serializability, and cascading, where cascading refers to child data being deleted or updated following an update or deletion of its parent. What happens when multiple transactions are executed simultaneously? The DBMS utilizes something called concurrency control protocols. Concurrency control protocols are what allow DBMSs to be as powerful as they are when it comes to handling queries for data. There are two types of concurrency control protocols, the first of which are lock-based protocols. These protocols can be one of two kinds. Binary locks are used for a data item that may exist in one of two states, locked or unlocked. The other kind of lock-based protocol utilizes a shared or exclusive lock. Shared and exclusive locks differentiate the locks based on their uses. If a lock is acquired on a data item to perform a write operation, it is an exclusive lock. Allowing more than one transaction to write on the same data item would lead the database into an inconsistent state. On the other hand, read locks are shared because data is not being mutated. For both of these types of lock-based protocols, a transaction cannot read or write data unless the appropriate lock is acquired. Let's move on to our next concurrency control protocol, time-stamped protocols. This protocol type is most common. While lock-based protocols manage the order between the conflicting pairs among transactions at the time of execution, time-stamped protocols start working as soon as a transaction is created. Every transaction has a timestamp associated with it, and the ordering is determined by the age of the transaction. Every data item is given the latest read and write timestamp. This lets the system know when was the last write and when was the last read. Now that we are familiar with the basics of transactions and how they handle concurrency, we can describe how to implement transactions. It's actually far more simple than one might think. Transactions are implemented using SQL queries and one or more servers. This visual represents the life of a transaction that either successfully commits its operations to the database or aborts its attempted state changes. We will now touch on transaction disadvantages. The primary disadvantage of transactions becomes apparent when there is an issue in a transaction. We must roll back any changes that we have made to the data and start from the initial state, rather than continue from the previous state, which results in wasted resources. Consider a transaction that modifies 10 rows in the database, but the 8th row causes an issue. A rollback is performed, reversing any changes made by the previous transactions. While extra use of resources is not great, it's not a bad price to pay to ensure the integrity of our data. And just what do we mean by the integrity of our data anyway? Data integrity. This term refers to the data in the database being accurate. One of the main benefits of the DBMS is its centralized control of data. This centralized control of data allows for administrators to define constraints on which transactions are valid for certain users. There is one technique that is widely known to provide data integrity. This technique, known as sharding, is the primary way in which we can ensure data integrity. Sharding allows the database to be partitioned into smaller datasets known as shards. What are the benefits of sharding? Well, for one, it makes the database smaller. It makes the database faster to query. It becomes easier to manage the database. And lastly, it reduces the transaction cost of the database. What would a use case in which we would want to employ sharding be? Consider a large company user database of 1 million users. Without sharding, when attempting to find a user, there will be a worst case of around 1 million transactions, which is slow and costly. Consider this same database divided into smaller shards of anywhere from 50,000 to 100,000 users each. Not only does it become easier to manage the database, the transaction cost is also reduced by a large factor that depends on how small each shard is. Let's move on to one goal of any reliable database, the ability to scale. Scaling alters the size of a storage system. It either compresses or expands the system to meet scaling requirements. Scaling can be achieved by adding resources to meet the expectation in the current system, adding a new system, or both. There are two types of scaling in database management. The first of these is vertical scaling. Vertical scaling refers to adding resources to the system instead of servers. Adding more power, such as a CPU and RAM, to existing systems are examples of vertical scaling. The other type of scaling in database management is horizontal scaling, and this refers to adding servers instead of resources. So when the existing system fails to meet the expected needs, and the expected needs can then not be met by just adding resources, only then do we need to add completely new servers. And so how do we know, how do these two types of scaling compare to one another? While horizontal scaling is easier to upgrade, vertical scaling is easier to set up, cheaper, and requires less maintenance. Our next core property in database management is data normalization. This is the term we use to describe the creation. This is the term we use to describe the creation of tables, as well as establishing a relationship between those tables according to some predefined rules. These rules are designed to protect the data and to make the database more flexible by eliminating redundancy and inconsistency. Let's move on to the stress-inducing part of the presentation. Uh-oh, that's right. It looks like we're having a data emergency. You need to store data for your application. What are your options? What are the benefits of each option? The first benefit, the first option is a file system, and the first benefit of which is its simplicity. File systems are far simpler to interact with and more accessible than a database management system. They also require fewer resources to use. Since it is far simpler than a DBMS, it uses a significantly smaller amount of memory than a DBMS. Additionally, file systems are not centralized, whereas a DBMS is. Due to it being centralized, when a DBMS fails, it impacts all users, unlike a single user's file system failing only for them. Lastly, file systems can be tailored for a specific software, whereas a DBMS works for all systems, so some areas of an application can suffer as a result. Let's move on to our other option, a database management system. This is the not so simple, but significantly more performant choice. Note that we will be considering database management systems as a general tool rather than discussing the pros and cons of various DBMSs. Starting us off, a DBMS provides us with the controlling of redundancy. Data redundancy refers to the same data being stored multiple times. We also have improved data sharing. The data is stored in one or more servers with some sort of locking protocol in place to ensure the same set of data is not changed by two users at the same time. Going back to a term from earlier, we have the advantage of data integrity. This ensures the data in the database is accurate. We mentioned data integrity previously, but it's so important that it's included again. Another great benefit of a DBMS over a file system is security. A database administrator, or DBA, has complete authority over the DBMS. This DBA has the ability to define authorization checks which will be performed following an attempt to access sensitive data. Next, we have data consistency. As we have already accounted for potential data redundancy, we reduce the opportunities for inconsistencies in our database. Since we are storing any given data only once, we remove the possibility of that data having multiple stored values. In terms of overall performance, DBMSs easily outshine traditional file systems. Another one we have is efficient access. And so let's look back at file systems in which files are indexed in place of objects. So query operations require entire file scans, whereas in a DBMS, object indexing takes place efficiently through database schema based on any attribute of the data or a data property. This helps ensure fast retrieval of data based on the indexed attribute. If you're like me and view everything in terms of time complexity, you can think of a file system as having an O of n lookup for some data, and a DBMS as having an O of 1 lookup, which is the obvious winner. Yet another great reason to use a DBMS is its enforcement of standards. Centralized data allows for an established set of rules to be defined such that a user may query the database if they do not violate any of these standards, including, but not limited to, naming conventions and data quality. On the subject of data quality, data independence helps to ensure data is up to standards. This is done by the DBMS providing the interface between the application and the data, the key being that the DBMS handles the task of data transformation, not the application itself. The last benefit of a DBMS is its reduced application development and maintenance time. DBMSs support many functions that are common across many important applications, which streamlines the development process and allows for resource allocation in other areas. Let's now take a step back and consider which parts of our data storage system are the most important to build around. What are the priorities when we decide how to store our data? Well, first off, your system needs to be scalable. Whichever tool you use for your data storage should handle load increases. These load increases should be handled smoothly up until some well-defined threshold. Next, your data needs to be highly available. It must survive hardware failure and network failure. Recall that transactions provided us with a tool for recoverability. Any attempts to access our data must be highly performant. In particular, the data stored in this system needs to be queryable with as close to single-digit latency as possible. Lastly, your data needs to be durable. Once it is submitted, data can never be lost. Now, what are some of the trade-offs that you need to be aware of when making these decisions? One important trade-off to consider is investing time and money in horizontal versus vertical scaling. As mentioned previously, it is far easier to scale vertically and add resources instead of servers, but the right answer for you will depend on the level of scale at which you aim to deliver available, performant, and durable data. Another trade-off to consider is when opting to implement sharding in your system. There are many important areas of consideration when weighing trade-offs in shard quantity, size, and categorization of data within shards that go beyond the scope of this talk. The general rule of thumb is that the smaller the shard, the more performant transactions with that shard are. On the other hand, fewer shards of larger size are more likely to ensure consistency and availability since there are less clusters in which the data can reside. That concludes our talk. Feel free to reach out to me on any of these platforms. Looks like we have time for 1 or 2 questions. Yeah, Jake.
Thanks, Leo. First of all, thank you so much for this great talk. I really appreciate it. So I actually am working on a project with a team, and we have implemented sharding to help with decrease the query time for accessing our data. And unfortunately, we have actually run into some performance issues when there's like big spikes in the flow of data. And I was just wondering if you had any, suggestions or ideas around that.
Thanks, Jake. That's a great question. So I love to hear that you've had success with your sharding with sharding in your project. It sounds like you might need to implement some additional logic to handle moving data between shards, as well as adjust your mappings to each shard. I recommend you look into a technique called consistent hashing. We don't have time to go into it now, so feel free to reach out after the talk. But in short, consistent hashing will allow you to assign data to shards in a way that is independent of your server quantity and the load on those servers. For instance, if one server goes down, consistent hashing will ensure that the drastic change in data flow is handled smoothly by redistributing data across the remaining shards. I hope that answers your question. Nader?
Hey, Leo, yeah, that's right. Jake's question got me thinking a little. If I wanted to store data and need to decide on a way to organize my clusters, is sharding always the best way to improve performance?
Whoa, Nader, love the great follow-up on Jake's question. So there are 2 clustering options that we usually choose from here based on the data being stored. So the first is for when we're storing a data set and it is too large to be stored in a single cluster's memory. In this case, our best option is to store different chunks of data across different nodes in the cluster. This is where the consistent hashing technique we just talked about would be a great choice. The second option is better suited for a relatively small data set where we can store the entire data set on every cluster node. Queries are evenly distributed among these clusters via a load balancer, since every node contains the same information. I hope that helps out. Thanks again, Jake and Nader, for the great questions. That's all the time we have today, but feel free to connect with me if you're interested in discussing any of this further.